going to change a little bit of tack, but we're still following on from that fantastic lecture by Michael Reeder in the last talk on heat waves, atmospheric heat waves, and it turns out that there are also heat waves in the ocean. They're defined a little bit differently, but we know that atmosphere and oceans are both fluids, and so they have some similar characteristics, but I think some important differences. And it's really, I think, an earlier time for marine heat wave research. So it's a pretty exciting time to work in this space because really we don't know a lot yet. And they're one form of ocean temperature extreme, just like atmospheric heat waves are one form of atmospheric extreme, temperature extreme. And marine heat waves affect, have impacts just like atmospheric heat waves. You can see there we've got some coral bleaching, arguably affects kelp. Okay, there's been evidence for oyster losses off Tasmania. There was a marine heat wave here in the Tasman Sea. Pacific oyster mortality syndrome. Salmon have been compromised and so on. And I'll talk about that as we go along. So the background, I'm going to start with a bit of background, just talk more broadly about extremes in the ocean, give you a bit of a recent history timeline and some impacts from recent events. And then I'm just going to give you the marine heat wave definition that was recently developed. And it's sort of along the lines of the atmospheric heat waves that Michael Reeder talked about, except the timescale's a little bit longer. I'll say something about characteristics and historical trends, some brief thoughts on marine heat wave drivers, and most recently some work on categorising and naming marine heat waves. And I think that in the context of what Hamish was talking about with tropical cyclones and anything really like that, how do you actually categorise or name individual events so that you can get some sort of a sense of the geography or the history of individual events, rather than just that it happened on a certain day and time, and then just a bit of a summary. So firstly, extremes in the ocean. I think probably the main extreme that we kind of really understand in the ocean is really sea level. And sea level extremes, I guess we're familiar with. You know, you go to sea, there's big waves. You go to the coast and we have inundation like what we see here at Collaroy. Okay, and the timescales of sea level change are really, I think, characterised at least some way by this particular figure here by Cathy McGuinness and others, where you can see that the contributing factors to sea level comes from even at the sort of the longer and broader scales from climate variability, maybe superimposed by tides, then weather events. Okay, so we're going shorter and shorter time scales from longer time scales and larger space scales, then to astronomical tides, maybe hours and days, storm surge, okay, things like weather events, east coast lows, tropical cyclones and so on, wave setup, and then wave run up all the way to there. So you can see that there's a sort of a cross interaction of scales, from large scales to small scales, and that actually affects sea level. And the drivers of those can come from climate modes, and I'll talk about that also in the context of marine heat waves. So this figure here just characterises the type of climate modes of variability that we might think about around Australia from the sort of higher southern latitudes associated with the southern annular mode. You probably heard about that in this winter school. El Niño southern oscillation, typically driven from the low latitudes here in the equatorial region. There's a mode in the Indian Ocean called the Indian Ocean Dipole, and Michael talked about the MJO this morning, the Madden-Julian oscillation. Okay. So there's also ocean temperature extremes, and it's only really been fairly recently that the phrase, I guess, marine heat waves has been coined. It hasn't really been used in the literature, but probably in the last 10 or so years it's really started to raise its head. In particular, I think it was really strongly coined in a marine heat wave that happened off Western Australia here in 2011, when the sea surface temperature was about 3 degrees or more warmer than average, and it had massive consequences on kelp habitats and fish species seen, tropicalisation of fish species, and I'll talk about that a bit later. We think about things like coral bleaching. Okay, so corals can tend to go white because they lose their biota that give them their colour, and expel those, and persistent, ocean temperature extremes can be important for those. But there's also an important thing to really understand in terms of this group and in terms of predictability is what really drives those marine heat waves. And this is just sort of a broad schematic of some events that have happened around the world. For example, the 2012 Northwest Atlantic event off here, which I'll talk about. Interestingly, the Blob off Northeast Pacific. So there's a name for a marine heat wave. The Mediterranean Sea one that coincided with the atmospheric heat wave that killed thousands of people in France and Spain and other countries during that time. So here's a bit of a history of those, and it's a bit of a timeline here. So here's the 2003 Mediterranean heat wave, and you can see the redness there. There was a marine heat wave here in the south higher latitude Pacific, Central Pacific, that coincided with a big El Nino event, Central Pacific El Nino event. The WA marine heat wave in 2011 that had very devastating consequences, as I said, for habitats and species off Western Australia at the time. That's been more recently called the Ningaloo Nino. North Atlantic marine heat wave that had impacts on lobster, the Blob here, 2013 to 2015, and the 2015-16 Tasman Sea marine heat wave that had quite strong influences on the aquaculture industry in Tasmania. So just running through those, in 2003 a record heat wave was experienced in Europe, and you probably, many of you will remember that. It was had devastating consequences for people in terms of an atmospheric heat wave, and people lost their lives. But associated with that was really, I guess, a top-down heating of the Mediterranean Sea down to probably less than 20 metres depth that was really, I guess, driven by anomalous air sea heat fluxes associated with atmospheric heat wave. And it had important consequences for rocky reef communities, and there's some papers there that I've actually put in the vertical there. Maybe you can turn it on your side when you look at your notes. I run out of space on my slide. But anyway, you can see the sort of characteristic SST changes that actually happened during that time in the Ligurian Sea and the Turanian Sea. Temperatures of 2 to 3 degrees warmer than normal. Doesn't sound like a lot, but when you think about the thermal inertia of the ocean and how much energy is required to heat up the ocean, it doesn't change a lot typically. Okay, when the atmosphere is changing a lot, the ocean isn't necessarily changing much, and a few degrees of anomaly can be really, really dramatic for species and so on in the ocean, or in this case, the Mediterranean Sea. The 2011 WA marine heat wave was another one that was about 3 degrees above seasonal values. It extended from Ningaloo at 22 degrees or so south to Cape Leeuwin down here. Quite a broad extent offshore, and it's more recently called the Ningaloo Nino. There are a number of things called Ningaloo Nino events. I won't go into the details of it here, but effectively the driver of that was really linked to the very strong 2010-11 La Nina event and regional wind changes that are actually happening here in the eastern Indian Ocean, that together I think it was about 2/3 La Nina and about 1/3 that gave it this characteristic Ningaloo Nino type driver representation. And one of the things that Thomas Wernberg said was that it really had noted significant observable impacts on biodiversity, including temperate seaweeds, sessile invertebrates, and a tropicalisation of fish communities, which means that they're basically swimming south. In boreal summer of 2012, there was another marine heat wave here in the northwest Atlantic that ran from the US through the Gulf of Maine and into Canada. And interestingly, it was a combined atmospheric warming and also changes in the position of the Gulf Stream that contributed to that. And interestingly, it had an effect on the lobster fishery, where the lobster catch, due to the way that they recruit, went up quite markedly. You can see compared with, in 2012, compared to, let's say, climatology, if you like. But you would think that that would be a great thing, but in fact it had a really negative impact because of the market just got flooded with lobster, and so the stock price actually went down dramatically, and it actually had a negative impact on that industry. And then this one here is a little bit of a complicated paper, but here we got the Blob in the northeast Pacific. This particular event ran from really, I guess, 2014, 13, 14 through to, it actually carried into the early part of 2016. And I just want to flag this paper. You're welcome to read it, by Di Lorenzo and Mantua. Mantua was one of the people who really, I guess, was the first person to show the importance of the PDO, if you've ever read that paper on salmon production in Alaska. And Di Lorenzo's done some really great work on North Pacific circulation and ecology. But basically, the event evolved through winter here with this warm blob here, and then extended down in the, I guess, autumn rather than fall. We're in the southern hemisphere, so we'll talk about it as autumn. In 2014, came around here, linked up with El Nino, and then basically came back. So he schematized this in terms of North Pacific oscillation forcing the upper ocean, generating a North Pacific gyre oscillation type pattern, which he talks about in his papers, if you ever read any of Di Lorenzo's papers, that actually connected through what they call meridional modes. It's like a coupled ocean atmosphere development here from the higher latitudes into the equatorial zone that linked up with the ENSO event during this time in 2014, and then generated atmospheric anomalies through Rossby wave train into the North Pacific again, connected up with the Aleutian low, modified the variance of that, and it turns out that there's a connection between the Aleutian low and the Pacific decadal oscillation, which again Di Lorenzo talks about. So you're welcome to read that, but he argues in this paper that there's this sort of persistent event, that it just didn't evolve and just hang around, but rather it actually connected from the high latitudes to the tropics, back up to the extratropics again, and therefore persisted through the following year and potentially into the year after that. So in early 2015, sort of what we saw as the really early days of marine heatwave understanding, we had a workshop at University of Western Australia with a group of people. Some of those I've already spoken about, Thomas Wernberg here. Jessica's done some nice work in Western Australia, Ming Feng on stuff about the Lewin Current. Eric Oliver is a bit of a star, working with me as a postdoc for a few years. And then also, this is Sarah Perkins Kirkpatrick and Lisa Alexander, who Michael talked about in his talk. They've done, I guess, some important work around defining atmospheric heat waves, characterizing them, and so on. So in effect, these guys in here, particularly, I guess, Sarah and Lisa, helped us to generate a marine heat wave definition that came from their background in that space. And then we've done some more work on drivers of marine heat waves and long-term trends, which I'll talk about briefly. But they're sort of, I guess, the key people in the physical space. But then this is really an interdisciplinary workshop that we had, and Marcus, I guess, from University of New South Wales as well. But Thomas is a marine ecologist, Dan Smale's a marine ecologist, these guys, this guy over here, Alastair Hobday's a fisheries ecologist, and so on. So it was a really nice connecting of the physics space and the marine ecology to try and get better understanding of their effects and so on. So this is the marine heat wave definition. So you would have heard in Michael's talk, he was talking about this 90th percentile above climatology, but in the atmosphere, because it's a bit faster, in effect, 3 days is nominally chosen as the characteristic time frame to define an atmospheric heat wave. In the ocean, because things are a bit more slow, a bit more sluggish, 5 days was the choice. And in this paper here, there's sort of reasons outlined why that 5-day was chosen. It's somewhat arbitrary, but it's sort of a bit characteristic. It's sort of a balance between what would be reasonable to get a good set of data and what we see as an extreme that persists. So here's the climatology, if you like, this blue line. And this is the 90th percentile. You can see it's seasonally varying, so it follows that seasonally varying climatological 50th percentile, if you like. And then anything above this threshold then, as long as it lasts for 5 days or longer, will be defined as a marine heat wave. These are just heat spikes, so they're short-term events, not really characteristic of marine heat wave. But you can see that basically they're defined by a start date and an end date. And this is really, I guess, the quantitative definition of what's over here is more of a qualitative description of what a marine heat wave is. Similar to the atmosphere, it's a prolonged, discrete, anomalously warm water event. Prolonged in the sense that it persists, discrete in the sense that it's well defined in terms of a start and end date, and anomalously warm in the sense that it's warmer than this 90th percentile threshold. So with that definition then, we can in effect unify our understanding of the ocean, and we can go back and try and maybe characterize things that people have done in terms of analyses across different sorts of data sets, and try to then, I guess, give an overview of marine heat wave history if we use a common data set globally. And one of those really, in terms of sea surface temperatures, would be AVHRR satellite data, where you've got fairly high resolution sea surface temperatures. They're gridded, and you can then apply that definition to, in effect, time series of maps and really understand marine heat wave characteristics. And that's really what's been done here. So here you can see we've got the three of the ones that I talked about. Here's the Western Australia one, here's the Mediterranean Sea event, here's the North West Atlantic one. And you can see over that period, or over these periods when those events happened, where at a particular point, you can choose any point on your map, that time history shows the marine heat wave events and characterises over time things like their duration, their maximum intensity, and their frequency, and so on. So that's the way that we approach it, and that's why daily data, at least, of SST from satellite is so useful for that. And you can see those events, and you can stare at these pictures and think about them in terms of past history and how long they last, what their maximum intensity was, and so on, across any point over your domain that you might like to choose, or otherwise you can average over particular domains and try and characterise it over broad areas. In some other work that came out of that group, we basically generated an understanding of the time history of marine heat waves in terms of trends. And so one of the things that you can see here, firstly on this left column, if I can, maybe I'll point to it here, it's easier for me to see. If you look at the overall means, you can see that there are frequency characteristics. Okay, this is just mean marine heat wave frequency as an average, mean marine heat wave intensity, and then duration. And there are some interesting characteristics. And then there's just broad sea surface temperature. Well, we know in the broad sea surface temperature case, we've got warm in the near the equator, cold towards the poles. But when we start looking at marine heat wave frequencies as averages and intensities and duration, you can see that the frequencies here in the equatorial zone are typically low. And you can see that there are broader characteristics maybe here in the Gulf Stream. You can see that marine heat waves seem to be more evident. In the boundary currents, maybe the East Australian current down here, and so on. And maybe if we look hard enough, maybe just leading into the Kuroshio and so on. But why do you think then the frequency of marine heat waves might be small, let's say, in that equatorial cold tongue? Anybody want to venture a guess? This is frequency per year. Well, because they, in effect, if you look down here, the duration of them, if I can bring it back, is effectively long in the zone where El Nino southern oscillation is strong. So in terms of that 90th percentile definition, you can see that in that equatorial zone, we get an El Nino event maybe once every few years. It's got to be sensitive to my finger. And therefore, they're low in frequency, but they last for a long time because the El Nino event actually evolves and hangs around, and so you can get into marine heat wave conditions for a longer time, even though they're less frequent. But on average, 2.5 days a year or 2.5 days a year or so. I sort of need a mouse. Or I'll just use this. Okay, so you can see the count, global average frequency and so on, intensity and number of days. And superimposed on that, you can see individual El Nino events, which are included here as the red ones and the blue ones. So we can see the trends globally. Okay, they're increasing over time from maybe around about 2 to 3 or 4. But you can see that on particular ENSO events, El Nino, La Nina events, you can see that there are peaks. So you can see that they're actually tied to modes of variability, in particular ENSO here. So there's a connection there, and maybe we can use that ENSO knowledge as a driver of understanding of potential marine heat wave events. And this one here just extends the record. So that one previous one was really just over the satellite record. Okay, so from sort of the early 80s through to 2016 or so. And then by using some representation of proxy from more monthly data, connecting that to the daily observations, we connected it way back to 1900 to try and understand a bit better the long-term trends in marine heat wave frequency and so on. And you can still see those ENSO events showing up, the extreme ones, 82, 83, 97, 98, and 2015, 2016. But overall, if you take those out, you can still see the trend is evident in the data. This one here, I don't really want to say too much about, but just to say that there's been really very little done in terms of understanding marine heat waves below the surface. And this paper here, done by Amandine Schaffer and Menina Rowan from University of New South Wales, just looked at 2 stations. One was the Ocean Reference Station, I think it was, ORS, and that's that one there, and also the Port Hacking station down to 100 metres, and just tried to characterise by, in effect, compositing a history of warming events through time, through months, to see how ocean temperature extremes were expressed below the surface. We can look at satellites and we can understand what's going on at the surface, but there's things going on below the surface that's actually hard for oceanographers to really get at because there's so little data below the surface. We rely on things like individual moorings like these ones. More recently, we have things like Argo at our disposal, Argo floats, which have been a great thing, but they move around with the currents, so don't necessarily give you time series. So in a way, the atmosphere is a bit easier to reconcile because there's so many observing stations in the atmosphere that we can look at. The ocean is very sparsely populated. People go out on ships, observations that don't necessarily follow the same track in that. So it's quite a complicated space in the ocean. So this is kind of a nice study to just show that you can see through time here, from sort of the early part of the year to the end part of the year, there is actually increased warming below the surface relative to the surface. And that's something that we didn't really understand before. So drivers. What drives marine heat wave events? Is that anybody's granddad? I hope not. Define drivers to be the set of causative mechanisms that combine to produce a marine heat wave event. And drivers comprise of local processes, Okay, so the things that we might actually try to understand from a temperature budget or a heat budget within a box. So you can see here, this is a classic kind of box where you might look at changes that occur above the mix layer. Okay, so you've got net surface heat flux through the surface that acts to heat. So, you know, short wave, long wave balance. Then we've got things like ocean advection zonally, so east-west and north-south. So these are ocean currents. Just the analogy in the atmosphere is obviously the winds. And then also what mixing terms are going on, like vertical mixing, horizontal mixing, and vertical advection through the base of the layer. So we can do that in terms of a sort of a heat or temperature budget analysis and look at the changes that occur in such a box. And the other thing that might be important to driving marine heat waves are the large-scale climate forcing mechanisms, like climate modes and how they teleconnect into the zone. So we talk about things like ENSO, SAM, IOD, MJO, and so on. So these are the climate modes that can potentially give us longer scale, time scale predictability. And effectively, the type of thing that Michael was talking about, well, he wasn't necessarily talking about climate modes per se, but he was talking about remote processes teleconnecting in through Rossby wave trains, okay, and affecting atmospheric heat waves that then locally would generate the processes that underpin the atmospheric heat wave, and in this case, a marine heat wave more locally. So all of those together are kind of the space that we might be trying to understand in the ocean. And here is that kind of temperature budget equation that we might use to reconcile this, where we look at the time rate of change of temperature balanced by horizontal advection, okay, there. And surface heat flux are probably the key terms in this, plus everything else, which is all the other stuff in there, the things that we might not be able to resolve, the vertical advection through the bottom and the horizontal and vertical mixing processes. And then the drivers, as I said, are really those climate modes and teleconnection processes that are coming, you know, that are going to basically inform the local responses to the changes in sea surface temperature anomalies that are expressed as the marine heat wave itself. So one case study then is the 2015-16 Tasman Sea marine heat wave, which is fairly recent. And this event was unprecedented for this region, for this part of the Tasman Sea here. It's a region where, for those people who aren't oceanographers, we get the East Australian current coming down the coast of east coast of Australia that's fed into by the South Equatorial current up here. And then it bifurcates away from the coast just north of Sydney, separates away across here as the Tasman front, but some of it actually extends southwards down here as what we call the East Australian current extension. And it's transports warm water further south, and it's really a succession of eddies, anticyclonic and cyclonic eddies, but the anticyclonic ones are the things that really warm the region. And this particular event that lasted for about greater than 8 months, went from September 9th, 2015 to May 16th, 2016. So it was way off the charts, 251 days. Previously, I think the big number was maybe 90 days or so. And it had a maximum of intensity of close to 3 degrees. But what it did do, it was really the first evidence of what we call the Pacific oyster mortality syndrome, where you get these black spots on the oyster and they die within basically 24 hours or so. So Tasmania is really an important aquaculture place for oysters, abalone, salmon and so on. So it has an important livelihood with regards to that. Salmon was performed poorly. The black-lip abalone were dying. They hadn't seen that before. And it was largely all due to this marine heat wave that happened. And these are just some of the bullet points of what really happened. The event occurred. It lasted for sort of greater than 8 months. To give a sense of the scale of the event, during the summer of 2015-16, temperatures were about 1 degree, greater than 1 degree above climatological averages over an area about 21 times the size of Tasmania. 2 degrees over an area about 7 times Tasmania, and greater than 3 degrees over an area about half, just to give you a bit of a sense of the scale. The impacts I've talked about, surfies were happy because they noted that it was warmer than normal, so they were out on the surfboards. Greater amount of out-of-range species. There's been a lot of talked about in terms of climate change, of fish swimming south, migration of species, and there was sort of species that hadn't been seen in the waters before. What caused the event? Basically, that paper that was referred to on the first slide showed that it was really due to the intensification of the East Australian current extension during that time. It was anomalously strong. It was the key term in the heat budget equation that was dominant for why that region warmed. ENSO was going on. There was a big El Nino event that happened at the time, but literature has shown that ENSO doesn't tend to have a very strong influence in the Tasman Sea, although we are convincing ourselves now that El Nino does play a role in this region, and as more evidence, and Eva's here, I think she's doing some work on this at the moment, is showing that there is some, although it's not as clear as the Lewin current, which is much more related to ENSO variability on the west side. And then here, in terms of a fraction of attributable risk analysis, I've just got some points there that basically showed that this event really was unlikely, highly unlikely to have happened without the influences of climate change. Okay. So what are the teleconnection processes? Michael talked about Rossby wave trains, and it's interesting that in the atmosphere, the Rossby wave trains seem to be an important role for atmospheric heat waves in the southeast of Australia. Oceanic Rossby waves also exist, and Rossby waves in the ocean hadn't really been understood as well as atmospheric ones because they weren't easily observable until the advent of satellite altimetry. Satellite altimetry has enabled us to show that sea surface heights vary over large scales. They're quite broad in scale in terms of lumps in the ocean, but the expression at the surface is only a few centimetres. So you could imagine, without having satellite altimeters with big pictures of how the surface of the ocean undulates, it's very hard to pick up. Below the surface, however, the thermocline, that part of the water column where the upper ocean changes from, let's say, very warm to cold over a very short vertical extent, undulates opposite to the sea surface. So when the thermocline goes down, sea surface height sits up, and it's by about 3 orders of magnitude. So if you're down 50 or 100 metres here, you're up by 5 to 10 centimetres here. Okay? And that's kind of the expression of the Rossby waves, which propagate west. So unlike in Michael's talk, where he talked about largely in the atmosphere, you're getting, particularly in the higher latitudes, you're getting very strong westerly winds. The Rossby waves are always going westwards, but they're getting sucked eastwards just by the advection, just by the flow. In the sort of latitudes of the subtropics through to the mid-latitudes, these Rossby waves basically go westward everywhere. Here's a Hofmolar plot of patterns of sea surface height anomalies across this section here. So you can see time going up here, and you can see these bands that are Rossby waves propagating westward in the ocean that are being picked up in effect by a satellite or can be expressed in data. One of the things about Rossby waves is, particularly here, one of the consequences is that they intensify western boundary currents. So the western boundary intensification that we see in oceans, for those people who are oceanographers, western sides of ocean basins are strong, narrow, swift currents, and over on the eastern side they're broad and slow. Rossby waves coming in can act to modify and intensify this boundary current. So this is a potential reason for why the East Australian current might actually modify its intensity over time, and could be a potential source of predictability for marine heat waves in the Tasman Sea, for example. Another thing is eddies, and so Zia Lee, an honours student of mine, was working on this. Zijier, he's in the, put your hand up there, yeah. So Zijier has been doing some work on looking at the role of eddies in the Tasman Sea, and how you might connect understanding of eddies, because the East Australian current extension is an important transporter of ocean eddies into this zone, and there's information within eddies that, particularly warm core eddies, that cause the sea surface to warm. Okay, so those eddies and those sea surface heights are in effect a potential predictor of marine heat waves some days in advance. And what Zigier was finding in his work was that you could potentially predict marine heat waves on the short timescales of the order of 7 days in advance using some sort of a statistical model. In the work that Zia was doing, showing that if you can start to take Rossby waves out further, you can track Rossby waves over many years potentially that can actually act to influence the changes in the East Australian current intensity. So the short and long time scale variations that we might understand. And the last thing I want to talk about is categorising and naming marine heat waves. And I guess this is really, how do you understand or be able to identify where and what a marine heat wave is? So here's some examples of categorising and naming anything really. If we look at formal naming, with formal naming and with category scale, hurricanes, for example, Katrina, like Hamish talked about this morning. Katrina is a name, and it was Category 5. So how are we going to identify what are the extreme marine heat waves? We've got marine heat waves, but what are the really big ones? Okay, tropical cyclone's an intense low, but then you want to know how big they are. And same way, what are the big marine heat waves? What are the smaller ones? Same sort of thing. How do we go about naming them? Storms, UK since 2015. Without formal naming, things like atmospheric heat waves, just a heat wave index, Beaufort wind scale, droughts, Palmer drought severity index. They're just ways of calculating but not necessarily naming. And then without category scale, fires, okay, so no category but just a name, Black Saturday, okay, so Michael talked about that. Droughts, the Millennium Drought, the Dust Bowl in USA. And then over here, things like hailstorms, although I do remember the Sydney hailstorm of 1999, that was a named hailstorm. So just ways of trying to understand where they are and what they are. And so this is what the group came up with whereas tropical cyclones are nice contained vortices in effect, marine heat waves aren't. They can be just blobs, they could be sort of spread out and so on. So the way that was proposed to try and categorise marine heat waves is to take the 90th percentile threshold as the threshold for a marine heat wave, which we've already got in the definition, but that in terms of the data, it's suggesting that this might be a good framework in which to work. So that a Category 1 marine heat wave would run from the 90th percentile to 2 times that difference from the 90th percentile to the climatology. And then a Category 2 would be from that 2 times to the 3 times, and so on. And with that kind of framework, then, we could have an event in time like this that runs through in time, and we can see over time as it evolves from a Category 1 to a Category 2, 3, 4, or not necessarily get there. So here's some revisit then of these marine heat waves that we've talked about. Here's a couple of them. There's the Northeast Pacific one, there's the Blob, and then we've got the Tasman Sea one down here. And you can see then when we overlay this framework, then we can start to see when they intensified to Category 2 or potentially Category 3 scale. Okay. And then when you revisit all the events, you can start to then show which ones were really big. And you can see this table then shows from Category 1 through to Category 4 that even though the Tasman Sea marine heat wave was really big in terms of its duration, 251, 252 days, it really only reached Category 2 intensity. Whereas the Western Australian marine heat wave, you can see, was out to a Category 4, so it was incredibly intense. And that breaks down there the proportion of days that it actually sat in those particular categories. And then I just really want to finish off then just by saying a few things about some ongoing work. So I think I'm pretty much on time. So ocean temperature extremes and marine heat wave predictability and prediction. So we're doing some work at the moment on ocean temperature extremes. So Eva, who's in the room, Eric Oliver and myself are looking at ocean temperature extremes in a NESP project where we're working with Terry O'Kane and James Rossby to look at, this project down here, using a decadal prediction system to try and understand, is there year-to-year predictability of marine heat waves using the CSIRO Access Decadal Prediction System tool. There's some work done on the Eastern Shelf using a shelf model in Progress in Oceanography, looking at overall predictability of marine heat waves. There's, as I said, honours student working on large-scale forcing of Tasman marine heat waves, where we're looking at the role of Rossby waves. And then ZGA has been doing some work looking at self-organising maps and how eddies can be used as predictors in the East Australian current tracking southwards for marine heat wave likelihood on sort of 7-day forecast timescales. There's been some work done by Thomas Froelicher and others. I believe there's a Nature paper in press. I haven't seen it yet, looking at projections under climate change. But overall, you can see there's a lot of activity, and a lot of these papers are very, very fresh. They're really only in the last few years. It's a very active and exciting space. And in terms of CLEX itself, there's just fantastic opportunities now within RP2, which is the heat waves theme, to do some process-based understanding of marine heat waves. Okay, so I would encourage you to think about that as your possibly an area of research that you might want to be interested to do. Finally, again, eddies. I guess I'm just revisiting this idea of eddies. So cold rings, you can see that they bring up cold water from below, reduce the sea surface height. Here's the warm core eddies. Sea surface height sits up and you get warming of the region. These are just projections, how you can see in a particular study of climate model changes under CO2 change. This is the, I guess in a model, I guess Tasman Sea and Southwest Pacific eddy field, at least that the model represents, using some sort of tracking algorithm. And you can see that for the longer lived eddies, this is the control experiment, this is climate change experiment, how warm core eddies are sort of increasing, at least in this model experiment, under climate change through the 2060s, 2070s, creating this sort of eddy avenue, if you like, down the east coast of Australia and bringing these warm core eddies into the zone and potentially increasing the marine heat wave characteristics over time. So to summarise, our understanding of marine heat waves is in its infancy. We now have a working definition to unify estimates of marine heat wave frequency, intensity and duration globally. They've been increasing in frequency, intensity and duration and are expected to continue to into the future. The drivers of marine heat waves include climate modes plus teleconnections and local processes like air-sea heat flux, advection and small-scale processes. We have little knowledge of the ocean subsurface or their dynamics, and we're really in the infancy of looking at marine cold spells, which you can apply the same definition but to the 10th percentile. So it's a great opportunity, I think, for CLEX to be working in this space. I'll leave it there. Yep.
The El Nino event, 2016, there was obviously a huge amount of coal bleaching in the Great Barrier.
Yes.
So what kind of, was there like a heat wave in that area as well?
Yeah, in 2015-16, yeah, there was a marine heat wave, and in fact, we found that 25%, I think it was 25% of the globe in 2015-16 was in marine heat wave conditions. 25% of the globe. So if you've got a kind of combination of trends, sea surface temperatures are warming up. So if we went back to those trends picture, just by virtue of sea surface temperature trends, it's basically tracking marine heat wave trends. So we've got this kind of superimposition of climate change in effect, increasing sea surface temperatures, plus the big extreme El Nino event of 2015-16, causing 25% of the globe to really be in marine heatwave conditions. So, and part of that around Australia was, that region of the Great Barrier Reef, which really happened in the early part of 2016 from memory. So it didn't really, because there was a mangrove dieback, some work we were looking at. There was mangroves that died back in the latter part of 2015, I think it was October, and so sea level dropped in the Gulf of Carpentaria dramatically, and mangroves around the Gulf of Carpentaria were basically just died off, and everybody's going, what's going on, what's going on? And then it wasn't until the early part of 2016 from memory that the Great Barrier Reef then really had that big bleaching event. So there's sort of an interesting timing issue of sea level contributions and that going on in the sort of upper part of northern Australia, and then the warming really hitting just in the early part of the 2016 time. Yeah.
I noticed when you were defining the category, you only looked at the intensity and not the duration of the event in defining the thresholds. Was there a reason for that?
The thresholds should be still there, I think, you'll find. So if we go back to that, you then go from, here's our time series, if you like. So you can see then for how long you're in that condition period.
Right.
So here, you can define your duration for how long it's in that part of the time series. So when it's red.
But you don't define the category as a function of how long it's in.
No. No.
Yeah.
No, it's only in terms of its intensity.
Right.
Yeah. And then the duration that it's in that intensity then is that reporting. Is secondary, that's right, yeah. Yeah.
It's possible to see the impacts of the marine heat waves on the formation, on the thickness of mixed layer or the formation of mold water?
Yep, I think, all of that would be interesting. So, I mean, I think, trying to wrap my head around things that we can be doing in our group, and, you could be looking at things like not only the ocean dynamic response to marine heat waves, like what you're talking about, like mode water formation and that, but also how ocean temperature extremes, persistent, then feed back to the climate. So then how does it trigger off anomalous weather patterns locally, particularly coastal ones? Is there a feedback to atmospheric heat waves? Don't know. I mean, it's so early. We've only had a definition since 2016, so plenty of work to be potentially done. Yeah. Yeah.
The heat waves in the El Niño region, do you define it as anomalous for all days or anomalous for El Niño days?
Anomalous for all days.
So then how do you differentiate between a marine heat wave and just the hot phase of a natural?
Because it's all done locally, so you're looking at every pixel on your globe is relative to its own 90th percentile. So that's why wherever you go over the globe, that will shrink or increase. So it's pixel by pixel. Yep.
You said the heat wave is discrete.
Yep.
Like a side.
Yep.
Is that just when it crosses the 90% threshold, or is it more complicated?
Yeah, that's right. It's if we go back to the picture, it'll become clear. There. So its start date is when it crosses that threshold, and then its end date will be when it crosses back. But there is actually part of that definition that says if it goes down and then comes up again within 2 days, it's the same marine heat wave. That's the only other thing. So that there's kind of a little bit of a hiatus for a short time, but it's not long enough for it really to say that this is a new one. So again, a little bit arbitrary, but that's the kind of working definition that we use. Yeah. Yeah.
So for heat waves that are precisely 5 days duration, do you find that those quite short heat waves have drivers that are different to the really, really big ones?
Yes, yes. So that's a really good question. So probably didn't tease that out enough. So you know, you could imagine that a surface heat flux type event, and if we go back to, let's say, the Mediterranean one, maybe it's not going to, it's going to make a liar of me, but is it there? Yeah, might make a liar of me. But so there's a marine heat wave off Tasmania that was going from like the late part of last year, and we kind of expected that the surface heat flux intensified one might just cause, you know, down to 20 metres, might just sort of disappear because it was just atmospheric force, whereas an advective one that's coming from, let's say, an intensified East Australian current that might be persistent because of some climate mode that's forcing it or something would really cause it to be much longer than, let's say, something that's atmospherically forced that might just disappear, right? But it seems like, and this is something that's, it's a really good question because I don't think we really understand this well enough yet, that even though you might heat from atmospheric anomaly, we found that even the surface heat flux ones can still sort of hang around, and they just kind of, even though it's only like to 20 metres, whereas the Tasman Sea one that happened in 2015-16 was like down to a few hundred metres depth, it still wasn't enough for it to dissipate. So I think the ocean just has the ability to sort of just hang on to things much more readily than, say, the atmosphere, which quickly dissipates. So we get a lot of marine heat waves that are sort of the order of maybe month time scales and longer rather than very, very short, that are really sort of not just a spike but something that's really connected to something that's more climatic, I think. And even that could be an eddy, right? The time scale of eddies is 30 days or longer, sort of month time scales. And if an eddy's going to hang around, like an atmospheric eddy's going to just go away in a few days, whereas an ocean eddy's going to just persist and just keep this heating for a much longer time. So I think the ocean timescales are just longer in general. And, but it's a good question. I think there's stuff that could be teased out there for sure. Probably not simple, but I'd say my punt would be the ocean advection ones are going to be the ones that are going to hang around more. Yeah.
You showed in one of the plots that there was seeing lower. There was more warming below the surface.
Oh yeah, the Amandine Shuffer one.
Do you have any? You said that it was surprising and
I don't know the paper well enough, and I think it's really early days for this. So this is just based on 2 stations, and the subsurface deepening of the heating is something that we want to do within CLEX. It's on my agenda.
Do you think that can be related to the duration of the wave that have been maybe a little bit like in the previous presentation?
It's got to be a dynamic response. It might be just something to do with the way that the thermocline is just sort of persisting and pushing up or something or down. Haven't really given it too much thought. So, you know, I mean, the atmosphere, you know, you might have just a dynamic response below the surface where the thermocline pushes down, and so in that gradient where the gradient's very strong, all of a sudden your anomaly below the surface is really sensitive to that and you get a really big response that's not necessarily expressed at the surface. Sort of get what I sense, because it's sort of warm up here, cold down here, and you're in that gradient region, and the moment that goes down, you know, you're going rapidly from warm to cold over a very short vertical extent. The moment that pushes down, it gets really, really warm just through a dynamic response. It's coming from the upper layer, but you're not seeing it expressed as a warming at the surface. You're only getting it expressed as a big warming below. And so the water column is really responding to it. Dynamically, that's what happens in ENSO, right? I mean, you know, you get in the Eastern Pacific, you get big movements of the thermocline up and down, and you can get, or Rossby waves are the same sort of thing. You're getting big changes in the subsurface temperature and salinity field just by virtue of movements of the picnic line. The which one? Oh, yeah.
So apparently, I mean, you've been talking a lot about eddies, and it is actually really important thing.
Yeah.
Right, it works. So I noticed that there's an increasing number of eddies that you're detecting in the second one. Well, I mean,
So in the climate change one, here's your sort of control, and then here's your climate change response. So you've got a kind of an intensification. We know that the East Australian current is intensifying in effect. And so this suggests that there's a characteristic, almost like eddy avenue, of anticyclonic eddies being pushed further south that are effectively warming.
But my question is, how does that intensify the marine waves? Do you know?
Well, it's really a sort of a blend between the time scales of eddies and the time scale of the sort of genuine advection. So, you know, really the East Australian current extension here is largely just a train of eddies, right? And it's these warm core eddies that are actually warm that bring warm water into zones that aren't normally experiencing it. So they'd be the type of warming that you would see would be on the timescales of the eddies, and the way that then moves that water into the zone.
So would you expect to have more marine heat waves in Tasman Sea?
Yes. Yep. Overall, yeah. Definitely. So there's this connection then between the Rossby waves that are maybe modifying the East Australian current extension, sort of on longer time scales, and then the time scale of the eddies that gives you the higher spatial scale predictability that you might see from the eddy itself. Because this is really the East Australian current extension is really that transport there largely. But it is, overall, it's affecting the whole system. Yeah.